in the discussion we have considered in the previous lecture, we have assumed that the virtual address is characterized of 20 bit address, which means the CPU is capable of generating a 20 bit address, whether there is physically that much memory or not. Now, 2 to the power 20 would mean 1 megabyte, that is as far as the virtual address space is concerned, or virtual storage space, or we may even call it as a disk address space, whatever it is. Now, physically in the memory we have assumed that 64 KB is available, which means essentially we have to deal with a 16 bit address, physical address. So, there is a translation of translation from 20 bit virtual address to 16 bit physical address. This is one aspect of it. Then we had also assumed a page size of 4 kilobyte. Now, for 4 kilobyte, essentially what you need will be 12 bits. Now, we were talking about virtual pages as well as physical pages, correct. Now, the CPU generates a virtual address. Why? Because in the CPU the program is loaded and the user has developed that particular program, and he has been given the impression that the address total address space available is 2 to the power 20. Now, he is not really bothered about, he should not also be really bothered about what physically that exists, that is why it is called virtual. Now, the unit that passes or what we were calling as a block in the cache, and here we are calling it as a page, right, in this particular one. The unit that passes between the virtual storage and the physical storage is the page. That is one full page will be getting loaded. So, you can see that in the 20 bit virtual address, the least significant 12 bits really will correspond to the will indicate actually the page size. In other words, this for the page size of 4 kilobytes, essentially you need 12 bits of addressing. Now, you call it a virtual page or a physical page, the same size, it is there. And so, as far as addressing any location is concerned, right, we must be able to address at the level of byte, is it not, whatever may be the page size, right. So, within a page what we are saying is there are 4 kilobytes. So, for addressing any location within a page, you need 12 bits, right. And so, this particular 12 bits will be called a page offset, which would remain the same whether it is virtual or physical. Here also it holds good, same thing. So, while translating from the 20 bit virtual address to physical 16 bit physical address in this particular example, you would find that the least significant 12 bit will not change. Why? Because it is the same page that goes from virtual to physical. Agreed? And this 12 bit essentially tells us which specific byte within the given page, that is what. Now, given that, so that is the page offset even in the physical address, right, page offset. Now, what about the remaining 4 bits in the physical address? What about the remaining 4 bits? Now, this particular thing will specifically tell what? The physical page number, agreed? The physical page number. Now, we have 4 bits, which means essentially we can have only 16 pages. This is what we were seeing earlier. So, this particular 4 bits will give you the physical page number, which means essentially what is physically available, that is in reality, is it not? It is what is really available, which CPU can access. The CPU may generate a different size address, but CPU can access only this particular thing, because that is what physically available there. So, 2 to the power 56 2 to the power 4, which means there are 16 pages. So, we have 16, we can call it as physical pages, right, because we are going to use the same term page both in physical and virtual. Now, that is about the physical page. Now, let us go to the 20-bit virtual address. We have 8 bits there, right, that is bit 13 to bit 20. So, 8, this particular thing will be giving actually the like this is giving physical page number, this one will be giving the virtual page number, right. This is the virtual page number. This is what actually we were talking about in the previous class also. That is, we have 2 to the power 8 because in the virtual address we have 8 bits remaining, and 2 to the power 8 that corresponds to 256 virtual pages, right. And at any given time only 16 out of these 256 pages will be available. This is what we were seeing in the previous class. Now, we must have these 2 bits of information. What is it which I was elaborating in the previous lecture. Now, which of these 16, okay, which of the 16 out of 256 pages, and second thing is, given a specific virtual page, what is that? 16 out of the 256 virtual pages will be in physical page. So, given a specific virtual page, where exactly it is, okay, where, in other words, where each of these 16. So, these are the things. CPU must know this, agreed, otherwise how can it proceed? The CPU generates an address and that address will give a virtual page number, right, and physically only 16 of the 256 are available. So, CPU must also know this, which of the 16, and given a specific virtual page where exactly it is. Now, why do we need this where exactly it is? Because we said it is meaningful that any virtual page, right, any of these 256 virtual pages, if you can load into any physical page, it gives some flexibility. Okay. Remember, in the cache we were not going for this kind of an arrangement. In the cache we are talking only about one specific arrangement, that is direct mapped, that is given a cache location, into that one of 3 or 4 memory locations, physical memory locations only will be available. Okay. Now, this is slightly different. We will take this issue again and then discuss later. Good. At this point maybe I would give a simple example, okay, for you to understand. It is like this. Supposing you have a book, let us say assume I have written a book by title Computer Organization. Okay. Now, you are going to locate this in the library. So, when you look for Computer Organization by Roman, this is the title, okay, you go title and author, of course, this information you have. Now, this book can be placed anywhere in the library, no, though it is not strictly anywhere, we may say, given a specific say 1 or 2 almirahs, it will be placed anywhere within those 2 almirahs, at least that, right, which I will just say anywhere. So, this is precisely what we have here. The virtual page is something like a book title and the physical page is the specific physical location where you can find that specific book, right, and it is meaningful to place a book anywhere, but not strictly anywhere. Okay, we will come to that because it is not going to be helpful. So, that is precisely what you have here. Okay. So, of course, those who can locate the book just by the title will be able to tell immediately go to this place and so on, but still the specific physical location can keep varying from time to time. Okay. Now, the fact that you can place a virtual page anywhere within the physical page Okay. That particular thing is in fact called the feature of relocation. That is, you are able to locate anywhere that you want. This gives quite a bit of freedom. Why? So, assuming, just give an example, assuming one specific memory chip is down, right, and that may correspond to a set of memory locations. So, in that case we can always bypass that memory chip, defective chip, and place our program anywhere, right, that way also it helps. So, locating, right, or relocating, that is a program when it is run, there is no guarantee that that program will always find physically only in some specific portion. You may be able to locate it anywhere, that is essentially called the feature of relocation. Good. Now, let us get back. We have this problem now. We can have only 16 pages out of the 256, and we also want this relocation, that is locating a virtual page anywhere. So, we also need this particular thing, where each of these 16. Now, obviously CPU must have this information. So, this bits of information and something more we can pack into it. This will be placed in a table, it is called a page table. Okay. That is essentially a table which will have enough entries, okay. A page table, a table which will have enough entries, okay, which will indicate which virtual page is available. Now, where precisely this page table will be? If CPU has to access, where else it can be? It can't be in the storage, right, and so it has got to be only in the physical memory, that is the DRAM, right. So, some portion of the main memory will be occupied by this page table. And what did we say? The CPU must always have the information which of the 16, which means basically that itself fixes the size of the table. What is it? The table must have 256 entries, agreed? It must have 256 entries, one for each virtual page, right. In that particular table, there is one entry for each virtual page. Now, by having some entries in that particular table, what are the things we can have? We can say whether that particular virtual page is available in the physical memory or not, okay, by having one bit, right, and then if it is available, then where exactly it is available, agreed, fine. So, a page table with in our case, right, 256 entries, okay, 256 entries, that is essentially these 256 entries, one entry for each virtual page, right, that is what it means, one for each virtual page. And among these 256 entries, precisely 16 entries will only be having a particular bit, right, which indicate that it is those 16 pages are available in the physical memory, and those for those 16 entries we can also add this information where exactly it is available. Okay. Good. So, that is the thing that we have got to introduce, right. I will just create, we have got to take a look at the translation of 20 bit address to physical 16 bit address. So, I will just indicate first the page table, which will be useful. So, let us say that is the page table, okay. So, that is the page table with, as we said, 256 entries. So, you must have 256 entries. Okay, there must be 256. And before we proceed further, how exactly the table is organized and then what are the contents. Okay. Let us have one more thing. Let us see one more thing. I said page table must be accessed by the CPU, and hence it will be in the physical memory. Okay. Now, if it is in physical memory, where exactly in the physical memory? Okay, again we are coming back to that. Should we reserve specifically some locations for this page table, in which case it gets fixed. For instance, with a different design, if you want to change the size of the this thing, for instance page size, suppose you want to change the page size, right. Suppose instead of 4 KB I go for a different design, let us say 1 KB page size. Then when I have 1 KB I can have many pages, is it not? Agreed. That is 4 times what I have, that is instead of 256 pages I will end up with 1K, which means 4 times this, the 1024 precisely. Then the page table must have as many as 1024 entries. Agreed? It must have 1024 entries instead of 256. So, which means there must be a way in which the CPU will know where exactly the page table starts, because the page table size can vary depending on our choosing the size of the page. Okay. Fine. So, there must be a mechanism by which we can tell the CPU that from a specific location the table starts, right. That particular thing is generally called a table origin, okay, register, which gives about it. Okay, that is a very general term. Essentially it will be called a page table register, which means it tells precisely where exactly the page table starts. So, really speaking it is a table origin register. So, it will tell the origin of the table. Okay, good. So, the contents of that will give some address, which essentially will point, okay, the contents of this, which will tell where the table originates. So, that will point to the start address, essentially it is an address, right, start address of the table. Okay. So, that it can be located anywhere, that is the idea. Now, where will this register be? Interesting, no, it is better we take a look at it. Generally a register is in CPU, right. So, this must be a part of CPU. Now, you can just see how exactly certain software considerations, memory hierarchy, all these things are influencing the design of the CPU also. CPU must have this register. This has nothing to do really with the user program execution. This is purely from the point of view of the system organizing, right, and making use of the different resources like memory, etc., right. So, you can just see the CPU which can say take care of higher level software features will have these extra things as part of their architecture, right. It has really nothing to do with the application program, and so this in fact is something from the point of view of the system program. Okay. Now, that is incidentally. So, there will be one register which is part of CPU, and that will give the start address of the page table. Okay. Now, you may ask me, right, How about the size of the page table? There can be one more register, right, which can indicate the size of the page table also. So on and so forth, the CPU's complexity can be going on increasing. Now, let us get to the page table. At least there must be one bit in this, right, one bit in this. There are 256 entries now. Okay. So, at least there is one bit in this. So, this in fact a typical, let us say that is a typical page table entry. And why did we start with page table? This is the point, right. It has got to indicate whether a given virtual page is in physical memory or not, and if so, where exactly it is. So, these points. So, one of these, right, bit will be indicating whether the particular, this particular bit I am talking about, one bit, right, whether the given virtual page is present in physical memory or not. Hence, this is called a present bit. Some people may call it valid bit also. Okay. So, one bit in this. Now, what about the rest of the bits? That is, let us say this is the present bit. Okay. Now, what about the rest of the bits? What should it give us? Essentially, it should tell where. Okay. We have 256 entries. So, one for each virtual page. So, given a particular virtual page, it should tell where exactly that particular virtual page is. Where can it be, right? How many physical pages are there? There are only 16 physical pages. So, it must give essentially an address, that is in this case a 4-bit address, that is specifically we are working on for this example. Okay. It must give a 4-bit address which will identify this physical page number. That is, now you can see you have this 8-bit virtual page numbers. So, these 8 correspond to 256. So, this 256 is what you have, starting from 1, 2, 3, 4 and so on up to 256, this is what you have, right. So, given a specific page number, the contents of that particular one will be actually this 4-bit. In other words, the physical page number will be available. That is what you have here, that is these 4 bits. This 4 bits is the physical page number. Agreed? So, this page table itself will be in the memory. Good. So, now given this, now let us complete this translation part, that is the essentially the 20-bit virtual address. Okay. So, 1 to say 12, that is 20. So, we have this 18 bits. So, this in fact is the page offset, and then we have the 16 bit. Okay. So, here is our virtual address and here is our physical address. Now, this part is the page offset. This basically this part of the address indicates just within the page. So, there will not be any change. So, whatever you have in the virtual address, the same 12 bits will be there in the physical page also. Now, this one which gives the virtual page number, okay, this part which gives the virtual page number, this we say indexes specifically into one of these entries in the page table. Okay. This is essentially some index. What index is it? What is it? Same thing. We have 8-bit 2 to the power 8, 2 to the power 8 256. Okay. So, in other words, you can see that from this particular address, right, it gives you this offset. So, if you go like this, so if this is 1, it refers to that, basically it is an offset within. So, the virtual page number specifically tells you which entry in the page table, agreed. There are 256 entries, one for each virtual page. There are 256 entries, one for each virtual page. So, that is in fact indexes, and now these 4 bits information, that is the physical page number, right, same thing, physical page number, these 4 bits. Now, these will be entered into this, right, agreed. So, this is in fact the translation procedure. Now, when does this hold good? It holds good only if the present bit indicates that this particular virtual page is in physical memory, which in other words this particular bit, okay, this must be 1, present bit if it is 1. When the present bit is 1 and the virtual page number will specifically index into the table, okay, will index into the table. By index, what you mean? It indicates which one of these 256 entries. Okay. So, it takes that particular entry and sees whether the present bit is 1 or not. If it is 1, then it means it is available in the physical memory. Assuming so, then this part of the table entry will give the 4 bit physical page number. Now, we say page is available in the memory. If the page is not available, this present bit will be 0, right. So, we can note that if present bit is 0, basically it means it is not present. In other words, what we say is page fault occurs, agreed. If present bit is not 0, then we say it is a page fault, meaning the virtual page is not available in the physical page, but where is it available then? It is available in the disk, it is not in the main memory. Okay. So, a page fault occurs. Now, compare this in cache, we are coming across, no, the CPU looks for something in the cache. If it is available, then we say it is hit, if not available, it is a miss. So, similar to this is why I said the cache we call miss, here we call it page fault, but the penalty is different, remember. Why? Because recall the figures, something like 20 nanoseconds and 100 nanoseconds, that is the speed difference between cache and DRAM. But between DRAM and the other one, this is, if this is 100 nanoseconds, the other thing is 20 milliseconds. Okay. So, the penalty that we were talking about miss penalty in that case, that will be much lower than the, if I may call it as a fault penalty. So, all right. Now, this present bit is a must, as we have seen why, right. So, there is one bit. Now, what harm is there if I add a few more bits, that is some more bits I can have? What? I can possibly have one bit which indicates that this particular page is only for the system's use or for the user use. That is, I use one bit for reserving the use of the page. I can have say another bit which says this page can only be read, you cannot write it. Okay. So, these are called something like access rights. Access rights, meaning only the system software has access to a particular page, the user cannot access it, and then you can restrict the user's access by saying these things like this particular page can only be read, can be used only for reading that page, read only, or you may say that particular page can be read or written, that is read or write. So, like this you can go on adding in this particular, that is an entry in the page table as shown here, only present bit is included. In addition, we can have other things. Now, by having these things, we incorporate the second feature we are calling, which is the protection, right. That is, by specifying access right, system use only, user use only, you protect the user from accessing the system's address space, okay. Because there are multiple users are there, the system software will be only one which supervises the whole thing, right. Multiple users will be there. So, we have got to see that the users indiscriminately they do not access the system's address space and corrupt that, right. So, this way you can implement the protection. Now, what is it we have seen here? Here we are seeing how exactly the address is translated, right. So, this is the translation process, and then by adding a few more features we can talk about the protection. Recall, we are talking about translation and protection. In other words, what we have seen essentially is the basic principles of memory management, okay. How exactly the memory is managed, okay. So, essentially translation and protection are two aspects of memory management. Now, you would see that in some systems that that there may be some special chips, right, special chips for incorporating this memory management, because it involves looking into something, reading from it, if not take some corrective steps in case of fault, miss and so on, right. So, you would find that in some systems you may be having special chips, they are called memory management unit, right, memory management unit, which essentially is a hardware solution for managing the memory, okay. Now, what has what is it we have seen so far now? We were talking about CPU generating an address, and what is the end purpose of this? The purpose of this is to access some word, maybe instruction, maybe data. Now, what is it we have ended up with? We have got to translate this address, and in translation what is it the CPU doing? CPU is looking into another location, because page table is in the memory, and from there it proceeds and gets another address, and then this address will have to be used. Minimum, as per this arrangement, we find that CPU, when it generates an address, it has got to look into the memory at least twice. Once it has got to look into the page table, this is one memory access, and then after it gets at the physical address, again it has got to look into the memory, right. Now, in two steps it actually gets at the address, but really it is not just two steps, some more steps are there. But now what has happened is, now this way now we are actually reducing the speed of the CPU memory access, is it not? This will have to be improved upon. So, there must be some schemes by which right now we have seen it is not just CPU placing an address and getting the data. Remember, this is how we started all our exercise. Now, the CPU places an address, gets another address and then it proceeds. So, minimum there are 2 steps involved, and what happens in case the page is not available? Something more. Okay. Now, we need to take a closer look at this translation process, which we will do immediately. So, when the CPU accesses the memory, we have seen that there are 2 steps. What is it? The first thing is, from the virtual address, make use of the virtual page number and index into the page table, and then the page table will indicate whether the particular virtual page is available in the physical memory, in which case it will have the physical page number, right. So, that will be used, and that in fact is the address. Now, assuming the page table, usually what happens is the page table sizes can grow bigger and bigger, because it is variable anywhere, right. It all depends on our page size, is it not? So, now the other arrangement is why that is the whole process is a translation process, right. Now, in this translation process, why all the time we have got to keep looking into this page table? Is it necessary? Now, recall the principle of locality. Normally, what happens? What did we say about the page? The page size is 4 KB, right. That is what we started, that is what we have been working out here. When the page size is 4 KB, you take one particular instruction. After that instruction is executed, normally the next instruction is executed, and where is that next instruction? There is a high probability that it is in the same page, agreed. Now, that is the principle of locality, right. If that is so, why this for the next instruction which is available in the next few bytes, if not next location itself, why keep looking into the page table? So, what happens is, instead of this particular thing indexing into the page directly like this, and from which we take the physical page number, anyway we need this, okay. Why not introduce another buffer arrangement? Okay. This is essentially a buffer arrangement, it has a special name, we will come to that. Some buffer arrangement which can hold, let us say, the most recently used a few locations, okay, which let us say holds the most recently used pages, information about those pages, okay, most recently used pages. What is that? Suppose a particular page has been accessed and we have got all this, that particular one. So, what is it we have? We have 256 pages. Now, arbitrarily we said most recently used pages. Let us say most recently used 32 pages, let us say, assuming, okay. It can be 16 or 64, whatever it is. Then what we say is, out of these 256 entries, the most recently used 32 page, those 32 things can be made available here, and this can be a fast memory, faster than the other one, the RAM itself, okay. So, we can have a buffer which holds information about the most recently used pages, let us say 16 or 32, in which case this virtual page number can index into this, okay. That is basically it is going to indicate this. So, from here we have got to see, and now there is a small problem, remember the page table has 256 entries, whereas here if it is only for 32 pages we have only 32 entries, agreed. but this may be faster one. And what this one can have is not like this particular thing that is it's okay. I think we can call this, what is this actually, it is coming in between this and the other one, and also 32 out of the 256 alone are available, right. This is something like a cache now, you can say, right. This is similar to the cache with which we are familiar, okay. Agreed. Now, how does this help actually? Now, this can help such that the moment the virtual page number comes, that indexes into the this particular buffer, and then if this particular virtual page is available in the physical memory, okay. It must be, because we have been talking about the recently used ones, but then there is also a possibility that it may not be, okay. So, we will look into the organization of these entries a little later, then in which case if it is available, then directly it will generate the physical address, okay. Directly it will generate a physical address. That is essentially what we will be having here is the required physical address, it will be directly having without any more translation. Otherwise, what happens here? So, it looks for the a particular entry in the page table, and then it takes this particular, okay, say what did we call physical page number, it takes that particular one. With the physical page number, it takes the other page offset and then generates the address. Instead, assuming it is a recently used page, okay, and it is still the page which is in use, okay, that information and all has got to be there. Then if it is so, then directly this one can give the physical address directly, okay. Some part of it can give the physical address completely. Now, what does this require? This particular thing requires, so that you take any entry, okay, there are 32 entries, you take any entry. I have already indicated what it must be. It is like a cache, is it not? And so, this will indicate this will have a valid bit, similar to what we had in the cache, a valid bit, and then after the after this particular, I mean in addition to this valid bit, what else? It will have to have another field similar to what we had in the cache, a tag field, because this tag is the one which will tell, right, because there are only 32 out of the 256 available here. So, the tag is the one which will indicate which, okay, that is 256 by 32, which will be 8, no. So, which of these 8 is available in this? It depends on the specific arrangement, okay. So, it is very much like a cache. So, as the CPU was making use of a cache, for translation also we can have a cache, and I was just calling it as a buffer, because it is specifically being used for translation. This particular thing is called a translation look aside buffer, or TLB for short. TLB actually stands for translation look aside buffer. That is precisely the function of that, okay. Just call TLB. Now, this particular thing is a reasoned arrangement in some of these processors, okay. It is very much like a cache. So, the virtual page number will index into the 32 entries of translation look aside buffer, and the entries here like in cache will indicate whether the particular thing is currently valid or not, and then it will also indicate which, okay, because it is only a subset 32 of 256, which of these is currently available here. If so, there is no more translation, this directly it will give the physical address that is required. Okay. This is what you may call as an architectural arrangement to speed up the whole thing, right. Now, this way there is no translation from this by looking into it and then concatenating, forming the physical address and then placing and so on. Okay. Good. Now, we have seen enough. Now, let us that is we have seen enough of the address translation algorithm. Now, why do not we take a quick look at what is happening in this address translation starting from the very beginning. Okay. What is it that we started with? The CPU generates an address, right, that is the virtual address, that is the CPU generates the virtual address. Now, let us look at the whole scenario. Okay. Let us not go into the details of how this and that. Now, from the virtual address, now which gives the virtual page number and the page offset. Okay. So, that is made use of, I am not repeating it, that is made use of to see whether there is a hit in TLB, because the translation look aside buffer is very much like a cache. Here also we can talk about a TLB hit and a TLB miss, right, it is not different from cache. So, first whether it is a TLB hit, if that is the answer will be yes or no, right. So, depending on if it is a hit, then what is it, read the page physical page address, physical address or the page number, okay, and concatenate and proceed. Okay. So, it say just say read physical address. Now, that is straightforward, that is the address is readily available, that is it is already available, because a hit basically means it is a recently used page, and so it is this translation has already been done, it is readily available. Now, if it is no, then we talk about a TLB miss, is it not? That is what it means, it is a hit, otherwise it is a TLB miss. Then there is no other way, one has got to go into the page table and page table must be verified, that is we have got actually page table which must be read, is it not, because it is not available here. So, it must read from the page table reading must go on. Now, the page table read, what is it? There are two things. The page table indicates whether that particular thing is present or not. Okay. So, depending on whether the page is present or not, let us say the page is present, okay, the other one page is not present. Okay. Now, why do not we take the easiest thing out? In case the page is not present, what is it? It is same as page fault occurring. Okay. Now, page fault occurring, then read from storage, that is what it is, read from storage, that is this one is not available in the main memory. So, we have got to discuss this issue later. Now, if the page is present, next, okay, if the page is present, that is this is available in the physical thing. So, well, you know what it is, what is it? Page is present, where do you go next? Read and check in the cache, because we should not forget, right, check in the cache, that is the page is present. Now, is it available in the cache, that is the next point. Okay, that is we say that the page is present, that is in the physical memory. Now, we go from physical memory whether it is in cache. Now, cache you can talk about cache hit or a cache miss, is it not? cache mean. Now, if it is a cache hit, then we say access the data. The data can now be accessed. Now, if it is a cache miss, yes, then access from main memory if the page is present, correct. Now, here again access from main memory. So, just put it as memory if page is present. Well, if it is not present, we know what it is, it is a fault. Okay. Well, this may have been indicated even earlier. Agreed. So, these are the various things that are involved, from the virtual address which the CPU places to the time the memory responds with data.